So today we are going to learn how to draw constitutional isomers in organic chemistry. Please recall that constitutional isomers are different molecules that have the same molecular formula but with different atom connectivities. And when we draw constitutional isomers, we are going to use bond line structures, which is very, very common in organic chemistry. Just keep in mind that bond line structures are actually more like a simplified version of Lewis structure. So that is why we should always respect the octet rule when we draw bond line structures. And also if we have any non-zero formal charges, and we are going to include in the bond line structures. However, since the constitutional isomers we are drawing are commonly for neutral molecules and non-zero formal charges are not common at all. So that's why you should try your best to avoid having non-zero formal charges. One really useful strategy is to consider valency of certain atoms. For example, oxygen, it is a divalent atom. So that means it will commonly form two bonds. It can be two single bonds or one double bond to remain neutral. And we try to avoid having three bonds on oxygen. It can be either three single bonds or one single bond and one double bond. In that case, we are going to have very unfavorable positive formal charges on oxygen. So since constitutional isomers, we have so many different possibilities, and certain strategies can be certainly helpful. So in this case, I would recommend to calculate the degree of unsaturation first. And we do have a formula, and that says we use the number of carbons times 2 and plus 2 plus the number of nitrogens, and which we do not have in this molecule, minus the number of hydrogen minus the number of halogen atoms, which we do not have either, and then divided by 2. So if we plug the necessary numbers in, and we will get the degree of unsaturation to be 1. So what does it really mean is that we may have either a ring or a double bond. We cannot have both. And we also try to speculate the structure and the functional group. I already mentioned we can have either ring or double bond. For functional groups, and the degree of unsaturation can provide some hint. The heteroatom, which are atoms that are not carbon or hydrogen, in this case it will be oxygen. That the heteroatoms can provide some hint of potential functional groups as well. Since we have only one oxygen, so it can be either alcohol or ether or aldehyde or ketone. Alright, so that means if the oxygen is singly bonded, it can be alcohol or ether. If it is doubly bonded, it can be either aldehyde or ketone. So once we speculate the structure information and then potential functional groups, and it's a very good idea to put them into different smaller categories based on the information we have, so that we will remember to explore all subcategories. So now what I did was, in this case, first I look at those two structural information based on the degree of unsaturation. So it's possible to be either a ring or double bond. So for double bond, we may have carbon-carbon double bond, or we may have carbon-oxygen double bond. And then we remember we also have oxygen, and that means for that oxygen we may have an alcohol or a ether. Alright, so that means we can have a ring and alcohol as our first small category, a ring and an ether, that is our second subcategory, and carbon-carbon double bond and alcohol as our number 3, and carbon-carbon double bond with ether as our number 4, and carbon-oxygen double bond can be either aldehyde or ketone, since we do not have many different possibilities in this specific molecule. And let me put them together as category number 5. So then for each individual category, we try to explore all different possibilities. Along the way, it is very, very important for you to notice some equivalent positions so that you don't have repeated constitutional isomers. And it should always, after you draw, and it's always a good idea to check octet as well as formal charges. Make sure that we do respect the octet and we do not have any non-zero formal charges. All right. So now we are going to use those categories one by one. So as I said, the first category we are going to work on is rain and alcohol. All right. So let me put it down here. So it is a rain and alcohol. Of course, in this case, the rain can be a 3-member ring, 4-member ring, and we cannot have a 5-member ring for alcohol. So for 3-member ring, and so since alcohol, it's OH, all right, so it cannot be part of the ring. So the ring has to be all carbons, and we already used 3 carbons, and we have 4 carbons. By the way, in this case, and we are going to treat the alcoholic group or the OH as a substituent. So we are going to focus on the carbon backbones, and then we add OH later on. So now for the carbon backbones, we already have 3 carbons. The 4th carbon can be added to any of those 3 positions, and you probably notice that they are actually equivalent. It doesn't matter where you put it, they will be the same. So let me put it on this position. So now we start to add our OH, and the OH, and for this one, we can add to this position. Now, it looks like a methyl, all right? And we can also add these 2 positions, but those 2 positions are equivalent. So no matter you add it here or there, it will give you the same constitutional isomer. The third possibility is to add to that position. All right, so that means the OH can be added to 1, 2, and 3 different positions. The reason why I call it 3 because they are going to end up with the same result. So now let's add those OH, and we can add a OH down there, and we can repeat what we are doing, and then we can add a OH down there, or we can add the OH down there. All right, so once again, if you put the OH at that position, and they are actually the same. So that's why you just need to show one instead of both. All right. So that is our 3-member ring. And of course, we may have 4-member ring. All right. So 4-member ring, and we are going to have 4 carbons to form a ring. And once again, alcohol, it can be attached to the ring, but itself is not possible to be a ring, as at least not being neutral and be part of the ring. So now you use 4 carbons to form a ring, and then your OH will be attached to one of the carbons. So those 4 positions are actually equivalent, and that will make, well, so you can add the OH to any position, and it will be the same. So that is our ring and alcohol. That is a 4-member ring. So now explore the rain and alcohol. And the second possibility, of course, is to have a rain plus instead of alcohol, and we have ether. So keep in mind that ether is, it has an oxygen that is sandwiched between 2 carbons. All right. So in this case, this oxygen can be part of the ring, and it's possible to be not part of the ring. So we are going to explore both situations. So if the oxygen is part of the ring, of course it can be 3-member ring or 4-member ring. So let's assume we start with a 3-member ring. So this is 3-member ring. We have 1 oxygen plus 2 carbons. Remember, we also have another 2 carbons, and those 2 carbons will be attached to those 2 carbons. We try not to attach to that oxygen, otherwise you're going to have 3 bonds on oxygen. It will have a positive formal charge, and we really don't like that. So for those 2 carbons, and of course you can add both of them at one position, or you can add one on one side and another on the other. All All right, so those are the two possibilities. And when you have, we can call it a cycloether, all right, so with another 2 carbons, all right, and this is a 3 membrane. And of course, we may also have a 4 membrane. All right, so now, once again, we explore the oxygen as part of the ring. We can call it a cycloether again. So in this case, you used 1 oxygen plus 3 carbons. And of course, we have a 4th carbon, and that 4th carbon, once again, try not to add to oxygen, but you can add to other carbons. All right, so when we add to other carbons, and notice that this position and that position, they are actually equivalent, and that one is unique. All right, so as a result, if you add a OH down here, no, not OH, you add a carbon down there, and versus if you add a carbon down there, it will be equivalent. All right, and then of course the second possibility is to add a carbon at that position. So those are the 2 possible cycloethers with 4 membrane. And of course, we may also have 5 membrane. So 5 membrane, that will include all 4 carbons plus your oxygen. Now you don't have any side branch like those ones. All right. So if we work on the 5 membrane, and we are going to use all of our carbons plus that oxygen, and this is the only possibility. All right. So now these are the possible ring and ether with oxygen being part of the ring. So of course, oxygen is not necessary to be part of a ring. It's possible not to be a part of a ring. All right. So in this case, what we are going to do, the only possibility is, well, you have a 3 membrane to account for that 1 degree of unsaturation, and you have 1 oxygen and 1 carbon left for your main atoms. And now, well, to make it ether, and this would be our only possibility. All right. So that will explore all our possible ring plus ether. So now for our third scenario, and it will be, let me write it down here. So we are going to work on carbon double bond plus we are going to have OH. All right. So once again, for this OH, it's an alcohol, and we can treat it as a substituent. So instead of focusing on this oxygen, and we focus on the carbons. So the strategy is that, well, let's focus on the carbon. We have 4 carbons, and of course these 4 carbons can be linear. All right. So in this case, the double bond, we add the double bond first, and then consider where we are going to add OH. So for double bond, we can add double bond at the first position, or we can add double bond at the second position, or we can add the double bond at the third position. By the way, if you add the double bond at the third position, or the third bond, carbon-carbon bond, it will be the same as that one. So that is why that's not something you don't want to repeat it. All right. So for this one, I just want to mention is some students may try this. What if we have this one? And they are indeed 2 different structures. All right. But we call them stereoisomers instead of a constitutional isomers because they have the same atom connectivity. All right. So that is why at this moment we just focus on one or the other, but not both. You can choose this one or the other one, the strategy will be the same. So now let's see, we are going to focus on this one instead. So these are the possibility if you have the linear carbons. We can call them linears because you do not have a branch. And the other possibility, of course, we do have a branch. All right. So now those 4 carbons will arrange like that. So of course our double bond, well, if you look at those 3 bonds, they're actually equivalent. So it doesn't matter where you put the double bond, and they will be the same. So let me put it down here. All right. So those are the 3 different carbon arrangement with, of course, our double bond. Now we can go ahead and add our OH. So for this one, we can add OH either at this the terminal double bonded carbon, or the inside double bonded carbon, or the one that is next to double bond. By the way, that is also called allylic position. And we may also add to the very, very right, which is far away from the double bond. So as a result, and we are going to have 4 different scenarios. So we can add an OH down here. Someone may say, well, can I add a OH down here? Yes. So in that case, it will be another stereoisomer, which is not the main focus in this video. So if you add to the second position, all right, so you add OH down there, and this will give you a separate molecule. They are different molecules, and you can try that. And then we have this scenario. So now we add to the allylic position. By the way, these two are called vinylic position. So, and we can repeat our carbon backbone, and then as I said, we can add OH at the very, very last position. So these are the 1, 2, 3, 4 different possibilities for this structure with OH. All right. And now we move on to our second. This we already have a double bond to account for our degree of unsaturation. We just need to add OH, just as we talk about. And for this one, you see, it's pretty symmetric. All right. So this position on the very, very left is actually equivalent to this position at the very, very right. So that is why we just need to worry about one side. Similarly, those 2 double bonded positions, they are equivalent as well. We just need to worry about one instead of the other. So now that will give us 2 possibilities. One is to add to the terminal side. The other one is to add to the double bonded side. Once again, this side is called allylic position. That one is called vinylic position. All right. So now we can go ahead and add our alcohols. All right. So if we add it to the allylic position, it will be over there. And if we add it to the vinylic position, and we are going to have this one. So those are the 2 possibilities. So now we move on to the third. So for this one, and if you look, once again, you will see some symmetry along this line, and then this position, all right, with single bonded, and this position, these 2 are actually equivalent. So now you can add OH either on this side or the other side. They will give us the same result. And of course, we may also add OH down here, but can we add OH at that position? Well, the answer is no. The reason is this carbon already has 1, 2, 3, 4 bonds, and you cannot add any additional bonds. All right. So otherwise, it will overviolate carbon. Remember, we should never ever overviolate carbon. All right. So based on what we discussed, let's see. We first draw the main structure, and then we try to put the OH. So now you can put it on there or here, it doesn't matter. And or you can put on where the double bond is. All right, so like this. Once again, try not to put in the in that position because it's already good with octet. We cannot accept any more bonds. So that is the third scenario when we have a carbon-carbon double bond with the OH or alcohol. So now we are going to explore our fourth scenario. So the fourth scenario is that we are going to have a double bond, a carbon-carbon double bond, and we also have a ether. All right. So ether oxygen, we commonly consider that one as part of your backbone. All right. So that is quite different from the alcohol scenario. So now ether, once again, don't worry about the double bond yet. Worry about the carbons and oxygen, and then you add double bond later on. All right. So in this case, ether once again is sandwiched by carbons, and what we can see is, well, we can put 3 carbons on one side of the oxygen, and then you have oxygen, and then put another carbon on the other side. All right. And in this case, well, those 3 carbons, we put them linear way, and of course, we may also have this scenario. That is oxygen. This is a carbon. Now we put those 3 carbons just like that. All right. So we can call this one branched. And the other scenario is, well, now we put 3 carbons on one side, 1 carbon on the other side. We have those 2 scenarios. And what if we put 2 carbons on one side of the oxygen and the other 2 carbons on the other side of the oxygen? All right, so those are the 3 scenarios. Someone may say, well, what if I put 3 carbons on the right and 1 carbon on the left, which will end up with the same as those 2. All right, so now we have those 3 we can call the backbone structures, and then we can try to add double bond. So for this one, when you add double bond, you can add a double bond down here or here, but try not to add a double bond between your carbon and oxygen in ether. Otherwise, you're going to have 3 bonds on oxygen. It will guarantee to have a positive formal charge, which is not something we want. All right. So as we talk about, and we can have 2 different places. We can have double bond either at the terminal position, or we can put it at this position, and we don't want to put double bond at those 2 positions. So that would be all the possibility for this backbone structure. So now we move on to this one. So once again, we don't want to add double bond at this carbon oxygen or this carbon oxygen. So we have those 2 bonds. We can put additional bond to make a double bond, and you probably realize these 2 positions are equivalent as well. So that means it doesn't matter where you put, and we are going to have the same result. So now let's see, I'm going to put it down here. So this, the only possibility from that backbone structure. So now we move on to this one. So this one, you will see it's, once again, very, very symmetric molecule. All right. And if you look at this one, and once again, we can have double bond for the carbon-carbon, but not carbon-oxygen. And we can add a double bond here or there, and these 2 are actually equivalent. So that is why we have only 1 possibility. All right. So that is our 4th category, and we have a carbon-carbon double bond with ether. So now let's move on to the 5th scenario. So that is, well, we don't have a carbon-carbon double bond anymore. We have a carbon-oxygen double bond to account for the degree of unsaturation. It also accounts for that single oxygen as our heteroatom. So for carbon-oxygen, and we'll say, well, let's put a carbon-oxygen down there. And then we try to add other carbons. Remember, in this structure, you already have a carbon down here and oxygen. So you have 3 carbons left. Once again, don't worry about a hydrogen. Never worry too much about a hydrogen. All right, hydrogen will work out automatically. So now for those 3 carbons, and of course, you can add them all on one side if you want. And of course, the other side of your carbon-oxygen double bond, you only have a hydrogen left. And this is an aldehyde. And of course, this is not the only thing we draw aldehyde. Remember, if you have 3 carbons on one side, it can be straight line or linear, or it can be branched. All right. So once again, I put oxygen, carbon-oxygen, I put a hydrogen down here, and on the other side, and we have those 2 bonds, and then we place another one. So now you will see you have 1, 2, 3 carbons, but now it's a little bit branched. So they are 2 different aldehydes. All right. So that is when we put 3 carbons on one side and only hydrogen on the other side, we end up with aldehyde. And then of course we may also try to place 1 carbon on one side and 2 carbons on the other, because the other carbon we already have in the carbonyl. So in this case, if we place 1 carbon on the right and 2 other carbons on the left, well, it turned out to be the only possible structure for our ketone. All right. So those are all the possible structures we can have. We already exhausted all our possible categories we can think of. So once again, it's always a good idea to double check your octet and double check your formal charges. And when you draw along the way, if you are already aware of octet or formal charges, and very likely you're good. All right. So let's see, we use this one as example. All right. So for this, there's a carbon down there, and now it has only one bond in our bond line structure because the other hydrogens we did not show yet. All right, so if you add those three to satisfy the octet, and that carbon will be good. So for this carbon, it's very similar to that one, and if you recall previously we mentioned these two carbons, this carbon and this carbon, they are actually equivalent, and once I add hydrogen, and you will see, well, both sides are methyl groups, they are indeed equivalent. The middle carbon down here, and it already has 1, 2, 3 bonds to achieve octet, so that means we have another hydrogen down there. So this carbon is already good with octet because it has 1 double bond plus 2 single bonds. This oxygen seems not to have octet yet, but keep in mind we did not draw out lone pair yet. If we do draw out lone pair, and that oxygen will be good as well. So now that would be our complete Lewis structure, except that I did not write the letter carbon. All right, and if you count the number of hydrogens, we have 1, 2, 3, 4, 5, 6, 7, 8. And as I said, when you draw bond line structures for constitutional isomers, you really don't have to worry about hydrogens, because hydrogens will play out automatically. If you check the formal charges, and since we are already conscious about valency, you are going to end up with 0 formal charges throughout. So let me recap. So when we draw constitutional isomers, because it can be so complicated, so many different possibilities, and it's a good idea to follow those a few simple steps. And number 1 is to calculate our degree of unsaturation, and then speculate, do you have a ring, do you have a double bond, or do you have other structures potentially? And then based on your heteroatoms and the degree of unsaturation you calculated, and speculate what kind of functional groups are there. And then based on the degree of unsaturation and functional group, and then try to create a table to outline all your potential subcategories, and then you can go ahead and explain all of them, explore all of them. All right. So that's how we draw constitutional isomers in organic chemistry, and I hope this will help.